Welcome back. In the last video, we proved that irrational numbers exist. Square root of 2, square root of 3, even Euler's number e, all irrational. But here's the problem we left hanging. How do we actually work with numbers we can't write down exactly? Think about it. The square root of 2 is somewhere between 1.414 and 1.415. But it's not exactly either of those. It's not exactly any decimal we can write. So how do mathematicians pin down something they can never fully express? The answer lies in two powerful ideas: the supremum, or least upper bound, and the completeness axiom. These are the tools that finally tamed the irrational numbers, 2,300 years after the Greeks first discovered them. Let's begin. Section 1.10, Upper Bounds, Maximum Element, and Least Upper Bound. Now we come to one of the most important concepts in real analysis, the idea of supremum, or least upper bound. This concept is absolutely fundamental to understanding limits, continuity, and essentially all of calculus. But before we get to supremum, let's build up the vocabulary step by step. Let's start with a simple concept: upper bounds. Definition: let S be a set of real numbers. If there is a real number b such that x is less than or equal to b for every x in S, then b is called an upper bound for S. We say that S is bounded above by b. Notice we say an upper bound, not the upper bound. That's because if b is an upper bound, then any number greater than b is also an upper bound. Example, the closed interval. Let me give you a concrete example. Consider the set S equals the closed interval from 0 to 2. What are the upper bounds for this set? Well, 2 is an upper bound because every element of S is less than or equal to 2. But 2.5 is also an upper bound. So is 3. So is 100. So is 1,000,000. In fact, any number greater than or equal to 2 is an upper bound for this set. Maximum element. Now, if an upper bound b is also a member of the set S, then we call it the largest member or the maximum element of S. We write b equals max S. In our example, the interval from 0 to 2, the number 2 is in the set. So 2 is not just an upper bound, it's the maximum element. There can be at most one maximum element. Think about it. If there were two different maximum elements, one would be bigger than the other, so it wouldn't actually be maximum. Sets without maximum elements. But here's the interesting thing. Not every bounded set has a maximum element. Consider the half-open interval from 0 to 1, including 0 but not including 1. This set is bounded above. 1 is certainly an upper bound, but 1 is not in the set. So what's the maximum element? Well, there isn't one. You might think, what about 0.9? But 0.95 is in the set and bigger. Okay, what about 0.99? But 0.999 is bigger. What about 0.99999? But 0.999999 is bigger. You can never reach a maximum because no matter what element you pick, you can always find a bigger element in the set. So we have sets that are bounded above but have no maximum element. What do we do about this? This is where the concept of least upper bound, or supremum, comes to the rescue. Definition 1.13. Let S be a set of real numbers bounded above. A real number b is called a least upper bound for S if it has the following two properties. Property 1. b is an upper bound for S. That's straightforward. Every element of S is less than or equal to b. Property 2. No number less than b is an upper bound for S. Think about what the second property means. It's saying that b is the smallest possible upper bound. If you try to use any number smaller than b as an upper bound, it won't work. There will be some element of S that's bigger than it. Uniqueness of supremum. Here's an important fact. If a least upper bound exists, it's unique. It's an easy exercise to prove this. Suppose there were two different least upper bounds, b1 and b2. If b1 is less than b2, then b1 is a smaller upper bound than b2, contradicting that b2 is least. Similarly, if b2 is less than b1, so they must be equal. Because it's unique, we can speak of the least upper bound. The term supremum is just a fancy Latin word meaning highest or greatest. We abbreviate it as sup, so we write b equals sup s. Examples: Comparing maximum and supremum. Let's look at 3 examples to really nail down this distinction. Example 1. S equals the positive real numbers. That's the interval from 0 to infinity, not including 0. Is this set bounded above? No. For any number you pick, I can find a bigger positive number. So there are no upper bounds, no maximum element, and no supremum. Example 2. S equals the closed interval from 0 to 1. This set is bounded above. In fact, 1 is in the set and is the largest element. So max S equals 1, and sup S also equals 1. When a maximum exists, the supremum equals the maximum. Example 3. S equals the half-open interval from 0 to 1, including 0 but not 1. This set is bounded above by 1, but 1 is not in S, so there's no maximum element. However, 1 is still the supremum. Why? Because, first, 1 is an upper bound. Every element of S is less than 1. And second, no number less than 1 is an upper bound, because for any number less than 1, I can find elements of S that are bigger than it. So sup S equals 1, even though 1 is not in S. This example shows the power of the supremum concept. It captures the idea of approaching from below even when you can't actually reach the bound. Section 1.11, the Completeness Axiom. We now arrive at what is arguably the most important axiom of the real number system. This is the axiom that makes the real numbers complete. This is the axiom that distinguishes the reals from the rationals. This is the axiom that makes calculus possible. Axiom 10. Every non-empty set S of real numbers, which is bounded above, has a supremum. Let me say that again because it's that important. If you have a non-empty set of real numbers, and that set is bounded above, then there exists a real number b such that b equals sup S. Why is this such a big deal? Let me show you with an example that reveals the profound difference between the rationals and the reals. Consider this set. S equals all rational numbers x such that x squared is less than 2. In plain English, S contains all the rational numbers whose square is less than 2. This set includes numbers like 1, since 1 squared is 1, 1.4, since 1.4 squared is 1.96, 1.41, since 1.41 squared is 1.9881, and so on. Now, is this set bounded above? Yes. For example, 2 is an upper bound. So is 1.5. But here's the shocking truth. If we restrict ourselves to rational numbers only, this set has no supremum. Why not? Because the right answer for the supremum should be the square root of 2. But we just proved that the square root of 2 is irrational. So if we only allow rational numbers, there's a gap where the supremum should be. The set of rational numbers is incomplete. It has holes. It's missing numbers. The reals are complete. But in the real number system, we have the square root of 2. The completeness axiom guarantees that our set S has a supremum, namely the square root of 2. The completeness axiom is what fills in all the irrational numbers. It guarantees that there are no gaps in the real number line. Every bounded set has a least upper bound. Always, no exceptions. Consequence for infimum. As a consequence of the completeness axiom, it follows that every non-empty set of real numbers which is bounded below has an infimum, a greatest lower bound. The proof is elegant. If S is bounded below, consider the set of all negatives of elements in S. This new set is bounded above, so by the completeness axiom it has a supremum. The negative of that supremum is the infimum of the original set S. Foundation for calculus. The completeness axiom is the foundation upon which all of analysis rests. Without it, we couldn't define limits properly. We couldn't prove that continuous functions attain their maximum values. We couldn't develop integration theory. Everything builds on this axiom. Section 1.12, Some Properties of the Supremum. Now that we know what a supremum is, and that it always exists for bounded sets, let's explore how it behaves. The supremum has some beautiful algebraic properties that we'll use constantly in analysis. Our first result is called the approximation property. Theorem 1.14. Let S be a non-empty set of real numbers with supremum b equals sup S. Then for every a less than b, there is some x in S such that a is less than x, which is less than or equal to b. What does this theorem say intuitively? It says, you can get arbitrarily close to the supremum from below. If b is the supremum, and you pick any number A that's less than B, no matter how close to B, there's guaranteed to be an element of S that's between A and B. The set S has elements that get arbitrarily close to its supremum. The proof is a beautiful example of proof by contradiction. Suppose that X is less than or equal to A for all X in S. Then A would be an upper bound for S. But wait, we're told that A is less than B. So A is an upper bound for S that's smaller than B. But B is supposed to be the least upper bound. Contradiction. Therefore, our supposition must be false. There must be at least one X in S with X greater than A. And of course, X is less than or equal to B since B is an upper bound. So A is less than X, which is less than or equal to B. Proof complete. The additive property. Our next result shows how supremums behave with respect to addition. Theorem 1.15. Given non-empty subsets A and B of the real numbers, let C denote the set of all sums x plus y, where x is in A and y is in B. If each of A and B has a supremum, then C has a supremum, and sup C equals sup A plus sup B. Example. Let me give you a concrete example to make this clear. Suppose A is the closed interval from 0 to 1, then sup A equals 1. Suppose B is the closed interval from 0 to 2, then sup B equals 2. What is C? It's all possible sums of a number from A and a number from B. The smallest sum is 0 plus 0 equals 0. The largest sum is 1 plus 2 equals 3. So C is the interval from 0 to 3, and sup C equals 3. And indeed, 3 equals 1 plus 2 equals sup A plus sup B. Perfect! How do we prove this theorem? Let A equal sup A and B equal sup B. First, we need to show that C has a supremum. Well, for any x in A and y in B, we have x less than or equal to A and y less than or equal to B. So x plus y is less than or equal to A plus B. This means C is bounded above by A plus B. So by the completeness axiom, C has a supremum. Let's call it C equals sup C. Now we need to show that C equals A plus B. We already showed C is less than or equal to A plus B. We need to show C is also greater than or equal to A plus B. Choose any epsilon greater than 0. By Theorem 1.14, the approximation property, there's an x in A with a minus epsilon less than x. Similarly, there's a y in B with b minus epsilon less than y. Adding these inequalities, A plus b minus 2 epsilon is less than x plus y, which is less than or equal to C. So A plus b minus 2 epsilon is less than C. This is true for every epsilon greater than 0. By Theorem 1.1 from earlier in the chapter, this implies A plus b is less than or equal to C. Combined with C less than or equal to A plus b, we get C equals A plus b. Beautiful. Theorem 1.16, the comparison property. Our final property relates supremums of different sets. Theorem 1.16. Given non-empty subsets S and T of the real numbers, such that S is less than or equal to T for every S in S and every T in T, if T has a supremum, then S has a supremum, and sup S is less than or equal to sup T. Intuition. This makes intuitive sense, right? If every element of S is less than or equal to every element of T, then the least upper bound of S should be less than or equal to the least upper bound of T. Think of it geometrically. Imagine S and T as intervals on a number line. If S is entirely to the left of T, then the supremum of S should be to the left of, or at most equal to, the supremum of T. The proof is left as an exercise for the reader in Apostol, but it follows naturally from the definitions. Section 1.13. Properties of the integers deduced from the completeness axiom. Now we're going to see something remarkable. The completeness axiom has consequences even for the integers. Theorem 1.17. The integers are unbounded. The set of positive integers, 1, 2, 3, and so on, is unbounded above. This might seem obvious. Of course the integers go on forever, right? But remember, we've built up the real numbers from axioms. We need to prove that there's no largest integer. And the proof uses the completeness axiom. We prove this by contradiction. Suppose the set of positive integers were bounded above. Then, by the completeness axiom, the set of positive integers would have a supremum, Let's call it a. So a equals sup of the positive integers. Now, by Theorem 1.14, the approximation property, there must be some positive integer n such that a minus 1 is less than n. But n is a positive integer, so n plus 1 is also a positive integer. And n plus 1 equals n plus 1, which is greater than a minus 1 plus 1, which equals a. So n plus 1 is greater than a. But wait, a is supposed to be an upper bound for all positive integers. We just found a positive integer, namely n plus 1, that's bigger than a. Contradiction. Therefore, our assumption must be false. The positive integers are unbounded above. The integers go on forever. Let's recap what we've learned today. In section 1.10, we discovered the supremum, the least upper bound that may not even be in the set itself. In section 1.11, we met the completeness axiom, the powerful statement that every bounded set of real numbers has a supremum. No gaps, no holes. In section 1.12, we explored the beautiful properties of the supremum, the approximation property, the additive property, and the comparison property. And in section 1.13, we proved something remarkable. The integers go on forever, using the completeness axiom. The big picture? The completeness axiom is what makes the real numbers complete. It fills in all the irrational numbers that the rationals are missing. This is the foundation of calculus. In future videos, we'll build on these foundations to explore the Archimedean property, sequences and limits, and eventually the heart of calculus itself. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.